today's lesson is on exponential functions, as you can tell. This is lesson 6.14 in your textbook. Take out your notes. Get ready to start writing some things down. What's that? I don't have any more people. Okay, we have a few goals for today. We might get through the first two. We probably won't get through all of these today, but here's a sort of an overview of what we plan to do in this next part of the unit. We're going to be able to identify exponential relationships, like we just did on our bell ringer, where we noticed that there was a constant rate of change in that it was growing by an equal factor rather than by an equal difference. So be able to classify exponential functions, be able to tell me if they're growing or decaying, right? You'll learn about that today. Looking at functions in the format of a table, an equation, and a graph, and to be able to compare the relationships between each representation to find key information. We should be able to evaluate exponential functions written in function notation, which you just did already, so I know you know how to do that. We'll just practice it. And then finally, I hope that you'll be able to graph exponential functions by making tables of values. So we have three different goals. Hopefully we'll get through the first 1 to 2, if not all of them today. Okay, so make sure you write this down because this is going to be some important information that we'll utilize throughout the lesson. But you need to understand the anatomy of an exponential function. This is a basic exponential function, and this is the format that all of these types of equations will take on, as well as the individual parts and what they represent. So take a few minutes to write that down, and then I'll explain to you what it all means. While you're writing this down, let's take a few minutes to discuss. First of all, whenever you're looking at a function, it's important to first think about what family of functions it falls into. And this type of function written in this format is called exponential. And the reason that it's an exponential function and not any other kind of polynomial function like we've been studying this year is because the variable, it's in the exponent rather than in the base. So the variable is up top, it's in the exponent, and that's what makes it exponential. The base number and this coefficient both take on real number values, and the variable is up here in the exponent as well as the output. The A value, which is going to take on the value of any real number, it could be positive, negative, it could be a fraction, a decimal, a whole number. But A is going to represent the initial value of the exponential function. So every exponential function is going to cross the y-axis at some point. Wherever it crosses the y-axis, that's where the x value equals 0, and whatever that output is, that's the initial value of the function, or the y-intercept. So you know that if x equaled 0, you would have something raised to the 0 power, which would be equal to what? to 1, and then 1 times a would be equal to a, right, or 1a, right. So we know that a is whatever the function has as its initial value when x equals 0. Okay, so that number here, a, it just represents the y-intercept, or the initial starting value of the function. The b value is the rate at which the function grows, or decays. Now, a function can increase or it can decrease depending on if you're multiplying or dividing, right? Now, we said we're always multiplying, but sometimes when we multiply by a certain kind of fraction, it ends up actually coming out to be a smaller number as a result of that multiplication, like multiplying by fractions that are smaller than 1. And so b takes on the value of how the function grows or decays, and it's dependent on what values b takes on, if it's positive and greater than 1, or if it's positive and less than 1. But do note that the value of b has to be positive. We'll explore a little bit more later on in this lesson why b has to be positive and it can't be a negative number. Does anyone still need time to write this down?
Mrs. Pisani,
Yes?
can you please send Victor Palillo to the office for dismissal?
Sure.
Thank you.
Bye, Victor. Have a good weekend. Okay, so I don't know that you necessarily need to write this down, but I would just like you to look at it and listen and try to understand the interpretation here. This is an example of how an exponential function could be used to model a situation that occurs in all of your everyday lives. How many of you have a bank account? Or your parents have a bank account, right? So everyone has a bank account or knows someone that has a bank account. Good. And you learned about this in business class too. Have you learned about compound interest? Do you know what it means when a bank account has an interest rate? What does it mean? Can I have one person raise their hand and tell me what they're trying to say? I hear a lot of mumbling. No? Bailey.
There's a set rate for how much it collects over a certain amount of time.
Okay. So it's a rate at which you increase the amount of money in your bank account? Is that what you're saying? Yes. So let's read this problem and we'll look at how interest rates actually affect the amount of money that you have in your bank account. Suppose you make an initial deposit of $300. Okay? We put $300 in the bank into a savings account, and the terms of the account are that it earns 3% interest and it's compounded monthly. What I did here is I wrote an exponential equation that models the situation for that compound interest, or the growth in your bank account, over X number of months. So looking at the equation, I sort of dissected it for you. X would represent how many months you've had the account open. So at 0 months, that's the day you open the account, you're going to have $300. That's how much money you put in. So the 300 represents your principal, or your initial deposit into the bank account. This number, we said, represents the growth factor. But notice that the growth factor doesn't involve the number 3%. Do you know why that is? It is written as a decimal, right? We always take percentages and we turn them into decimals when we want to use them in an equation. But look at my calculations here. I said the new balance is found by taking 100% of your previous balance plus the 3% interest, but the 3% interest gets divided over 12 months. Did you know that? Then when it says it's a 3% interest, APY, or what is it called, AYP on your account, that would be divided over the number of times the interest is compounded in a year. So because 3% is compounded monthly, that's 12 times in a year that you're going to earn interest. So you divide the 3% by 12 months, and that comes out to only be 1/4% interest that you get each month. So even though it says 3%, every month you only get 1/4% interest added on to how much money you have in the account at that end of that month. So 101/4% would represent how much money you're going to increase your balance by at the end of every month. So if we take this 101/4% and we turn it into a decimal, we would move the decimal place 2 points to the left, in other words, divide by 100, and we would get the decimal 1.002 0.25, and that's where this number comes from. Okay? So I did 3% divided by 12, that was 1/4%, and then I added that on to 100% and moved the decimal point to make it into a decimal. So this all looks nice, right? It fits the format, but it's still not that easy to just see how much money do I have. So what you can do is you can use your graphing calculator. Do you have one with you today? If you don't, I have some you can borrow. We're going to go into the graphing calculator, go into the y equals screen, and type in the equation that I just gave you. The two of you can just share one between you because I don't have everybody.
I haven't used one.
You guys just share one. Go. Will you guys share a calculator? You all have one? Nothing to eat. Sure. Hopefully this one works. Remember, if you want to clear out the calculator before you get started, you push second plus 712, and then that sort of resets all of the default settings. So I went into y equals, and I typed in my equation. I had previously entered that, but you can enter it now. And now if you push second and then graph, it brings you to the table. So this is a nice feature that the graphing calculator can help us with, because when we want to generate values quickly for a function, we can type in the function's value into y equals, go to the table setting, and then it gives us a bunch of input-output pairs right there in the table function. So let's interpret what this table says. What did x represent in the equation?
The number of months.
The number of months, right? The number of months since you opened the account. What does y represent? Yes, the balance in the account. So when I see the ordered pair 0, 300, what does that represent?
On the first day,
Yeah, and the first month, like before time has started, at the very beginning when you deposit the money, you have $300. After 1 month passes, now you have $300.75. How did we get that number?
After the first month, the interest rate went up, something like that. The interest rate went up, so you got 75 cents.
The interest rate didn't go up. The interest rate was just applied to your balance. So if you take that 101/4% and multiply it by 300, what do you get? 303/4. Okay, does that make sense? So that's why we have 303/4 in our bank account, because we multiplied the growth rate by 300, our initial amount. Now if you take the 300.75, or the $300.75, and multiply that by 101/4%, you're going to find out that after 2 months, you now have $301.50. Big whoop, right? You could find that much change on the ground. It's not really getting you that much money after 1 or 2 months, but as time goes on, you can see your money is growing. After a year, you have $309.12. Okay? You didn't do anything, you just put your money in, let it sit there, and it's growing. It's compounding. That's kind of cool, right?
Free money.
Free money. Just don't touch it. Don't take it out. After 2 years, you have $318.53. How come it's not growing that much? Well, it's a low interest rate, right? So it's not growing very much because it's a low interest rate. What else attributes to the fact that the money's not gaining that much more money? Kylie? You didn't deposit very much, right? You started with 300 and you haven't added in. If you wanted your money to make more money for you, you got to keep putting money in the bank, right? Just leaving $300 to sit there, it doesn't make very much money. I was talking to Mr. Grant today. He said, I think it was like 10 years ago, he put $10 in some Federal Credit Union account. Just put it in there and let it sit, and he got a bank statement that said he now has $10.03. But yeah, it made him no money at all. It was like a terrible interest rate. But so if you just let the money sit there, you don't make that much money. But you can think about how you could make more money is what if you had more money in the account to start with. So instead of depositing 300, what if we deposited like 1,000? Right, let's look at how that would change over 2 years. Remember we earned $18 approximately over 2 years for depositing 300. But if I deposit 1,000, after 2 years I made $61, right, on my initial deposit. So depositing more is also going to grow faster. So your initial rate has something to do with it. Okay? Do you have any questions? Are you all right with using the calculator to input these functions? Did anyone have a question about how to get the function or the table into the calculator? No? You're good? Okay, good. All right. So let's look at a few examples that aren't so complex, right? Because the compound interest equation was a little bit complex. It had fractions or it had decimals and percentages in it. Here are some basics, just so we can get sort of to the roots of exponential functions. I would suggest you write this in your notes. You've got a side-by-side example of exponential growth and exponential decay, so you can see the differences between the two. And you should be able to recognize the differences based on a graph, an equation, and a table. And we'll fill in the table in a moment so you can see the differences. I would like you to start using the language of growth and decay for these types of exponential functions so you get used to classifying them the way that mathematicians classify them. I would draw an example of each graph. You will find, just in today's lesson as we look through several different exponential functions, that every exponential growth function has a graph that takes on the same characteristics. What do you notice about this graph? Tell me some descriptions you would give this graph. Okay, it's called exponential. It's growing. What do you mean by growing? It's increasing. From left to right, it goes up. Does it go up at a constant rate?
No. Well,
Does it have a constant slope? Let me ask you that question. No, it doesn't have a constant slope. Brennan, what did you notice? Yep, that's the same in math. Anytime you have a graph, if it's going up from left to right, that's increasing. And if it's going down from left to right, that's decreasing. Yeah, good. So you're seeing the similarities between both classes. So if you look at very small values of x, like numbers less than 0, you can see that from point to point to point, the numbers are not increasing very much. They're going up, but they're going up by a very little fraction. But then once we get onto the positive side, for x, all of a sudden from 1 to 2 to 3, the numbers start growing very, very rapidly. They're not growing at a constant rate. There's a constant growth factor. They're multiplying. They're doubling each time or tripling each time depending on the function. The values of the function are increasing from each individual value of x. Take a look at the equations. Remember the dissection of the equation? What did this number represent? A, which represented the initial value. In other words, the y-intercept. The y-intercept, right here, is the point where the graph crosses the y-axis. What ordered pair would you associate with that point? What ordered pair?
0, 2.
0, 2.
For that
Good.
graph,
Yes, for that specific graph, we would put that point at 0, 2. So if I identified that this number represents the y-intercept, which is 0, 2, where would I plot that point in the table? Where x equals 0. Good job. Put the 2 right there. So I'm going to show you a shortcut for how you can make the tables for these functions without having to evaluate all of the exponents. If this is the y-intercept, we put that in the table where x equals 0. That's what the y-intercept did. Now this number, 3, do you remember what that represents? Yes, the growth factor. Good. What operation does the word factor mean? Multiplication. Good. So if the growth factor is 3, it means that the function multiplies by 3. So if this output represents 2, and I multiply it by 3, the next output is 6. And then if this output is 6 and I multiply it by 3, what's the next output? 18. So we can see that if there was, x equal 3, then the next output would be, can you do 18 times 3 in your head? Hold on. 54. Good. All of a sudden the numbers are going up really fast. I'm not going to ask you to do 54 times 3 in your head, although you could. But you see that the numbers just keep multiplying by 3. So now if I wanted to move backwards in the table and find out what are the values for the negative inputs,
Divide by 3.
divide by 3. Very good. So if we're multiplying by 3 going down the table, we divide by 3 going up. So if this output was 2 and I divide 2 by 3, how could I write that? Say that again. 2/3. Good. 2/3. And now if I take 2/3 and I divide it by 3, say that again. 2/9. How'd you get it?
You divide 2/3 by 3 again, and then you basically multiply what you're dividing it by.
You multiply the denominator by 3. Exactly. So we take the denominator, 3, we multiply it by 3, and that gives me 2/9. If you took 2/9 and multiplied it by 3, you would get 2/3. Let me just demonstrate that, because if you're not all on Joseph's head right now, you might not know what he's talking about. If I take 2/9 and I multiply it by 3, or 3/1, we know that that gives us 6/9, which simplifies to 2/3. Right? We were just reversing that process. And then if you take 2/3 and you multiply that by 3, you get 6/3, which equals 2. Right, so you can see that from each output, if you multiply by 3, you get the next output. That's called a recursive relationship. Did you have a question?
Yeah, on this one, where's the FD button? Let me put this up.
Oh, you go to math and then hit fraction. Okay, so we were able to fill in this table without having to plug in all the exponents and evaluate them. We could use the relationship of the growth factor of 3. All right, so let me get some of this out of your way. Let's do the second table. First of all, this number is the y-intercept, right? Yes, we all know it's a 2. More specifically, it's the y-intercept. The two graphs have that in common. Where do I put the 2 in the table? Next to 0. And now the growth factor is not 3, it's 1/3.
So would the growth factor, never mind. I was just gonna say the growth factor for, the first table is 30, because 30.
Yes, yep. So this growth factor was 3, which means we multiplied each output by 3 to get the next output. Here, the growth factor is 1/3, so we take each output and we don't multiply it by 3, we divide it by 3, right? So 2 divided by 3 would give me 2/3, and 2/3 divided by 3 would be 2/9. Looking kind of similar to that table. So if I work backwards now, instead of dividing by 3 to go backwards, I multiply by 3 and I get 6 and then 18. And you can see that if you did 18 times 1/3, that would be like dividing by 3, you'd get 6. And 6 divided by 3 would give you 2. And so it's a constant growth factor. But this time, instead of growing, it is decaying. Okay? It's decaying. Think about what you're learning about in science with radioactive decay and half-lives.
We didn't do that yet.
Haven't done that yet? I heard you were starting it. You might be seeing it soon. You haven't learned about half-lives yet?
Oh,
Very soon, very soon. Because I know that Miss Avril and I always do this unit right around the same time, so you see the same thing in both classes. All right, so decay means to decrease, and you'll learn about it in science, but radioactive decay is when an isotope divides in half. So the number of organisms that are there, they divide in half after a certain number of time, right? And then they divide in half again, and they divide in half again, and so it's the same thing as what you're seeing here, except this is dividing by, or I'm sorry, multiplying by 1/3 or dividing by 3 each time. Look at the two tables. How are they similar?
It's like an opposite flip.
It's like a flip, like an opposite. Okay, so we're seeing that they're inverses of one another. This function is increasing, this function is decreasing, but at the same rate. Can you erase all this? How are the equations similar?
Like what's the same about them?
Yeah, what's the
Just
same
the
about them?
two.
They both have the 2 in common?
Well, even 3 over 1
3 over 1 and 1 over 3. They are reciprocals. Good. So they are inverse operations. This one's multiplying by 3, this one's dividing by 3, and so then you end up with the same outputs except in reverse. That's why this graph and this graph are mirror images of one another. Didn't see that coming. It's like the big finish. Alright, so let's utilize our calculators again. I want you to do a little bit of an investigation. On your calculator, I want you to take this equation. We're going to let A equal 1. You just want to simplify it. And we're going to take the B, and I want you to just test out some different positive values for B. Test them out in your graphing calculator. Look at the table, look at the graph, and tell me for each value of B that you try, is it growth or is it decay? And what we want to try to do is come up with some kind of generalization for what makes exponential growth and what makes it decay for B. What values of B are going to cause that kind of relationship? Then I want you to see if you can find any values of B that don't work. Anything that breaks the function, where it doesn't make exponential growth or decay. See if you can figure out what values don't work in this function. Okay? I'm going to give you about, I'm not going to make it 8 minutes, we'll do like 6 minutes. You can test around with a partner, right? Work with somebody next to you and see if you can explore on your calculator.
So we need to add a random number into the B.
Yes. Yep.
No.
I found one that doesn't work.
So up here, type in 1 times, or you don't even really need the 1. Whatever number you're going to pick, let's say we pick like 5 to the x, and then change that 5 to different things, and see what happens when 5 takes on different, or when B takes on different values. Look at the graph, look at the table. Well, we're all the way up at 18, we'll go back to 0. And then tell me, is that growth or decay?
I found out by my graph.
Were the plots on? You have all kinds of stuff. Get rid of that. Do second plus 712, and that will clear out the memory. Yes, sir. Oh, yeah. Oh, because yours is a newer operating system, and so it just makes it an exponent. Remind you how to put the caret in. Just type that. X for the exponent.
Alright. Sounds good.
Second graph. Yes, sir. That is not correct. Wait, so you found one of the values that don't work. Let me go back to the questions. See what I wanted you to answer.
Oh, no. It looks like the growth rate is like slower.
Well, it depends on the factor. The factor 900. Yeah, that one probably you can't even see. I bet it just looks like a vertical line. Yeah, exactly.
It's one doesn't work.
One doesn't work?
Well, it's one, all of it's right.
Okay.
And zero. Yeah, that, and then correct. Error. No, you have to second then you're out.
You have
Is this your calculator? Your window was just, it was set to like 77 instead of 10 to 7. Turn off your plot one. Go up there and hit enter on plot one so then.
Yeah, you're supposed to change. Yeah.
Okay. Have you tried only integers? Okay. Try something different than integers. You wrote 9x, not 9. Now let
I was already somebody your turn class. She walked up like right behind. She was like standing next to you when you did it too. No. That's why Eric showed up.
Well, there you go. She loves it. I tried to play
That's why Eric showed up right there. That's why he did.
What are you supposed to be doing right now? Testing several values of B. That's an interesting conundrum. You just typed in what? 0.9999999. What is 0.9 repeating equal to?
Yeah, I know. He did the same thing for us.
Well, repeating decimals have a denominator of 9. So if you have 0.9 repeating, then you have 9 over 9, which is equal to what? So it's just like entering in 1 to the x, right? Nine's almost up. Take your last guess.
Yeah, 1 times 9.
Wait, Shane, is this her?
That's what I was, he was just doing that, yeah.
Class.
And then when Walker. We're not allowed to announce it.
Look at this mirage
They're not going to cross.
Do you know what the E is for? Yeah, it's scientification.
No one's allowed
So
to
it's
cross
saying
until bus riders.
1 or -2 with 16. Yes.
She said,
Time's almost up. Prepare for a loud noise. No, there's not today. Alright, ladies and gents, let's bring our attention back up to the front so we can summarize what we found from the exploration. First of all, I asked you to test out some positive values of B. Tell me which kind of values of B you found growth and which ones made decay, and then where were the values of B that sort of broke the function and didn't work. So answer one of those 3 questions. Tell me what you came up with. Brendan? 98 for B was which one? Growth. Okay, so when B equals 98, we had growth. Okay, what else? What other values led to growth while we're on the growth topic?
20.
20. 6. Ooh, okay, so we're finding a generalization, any number above 1.
Yes.
Does that mean only the integers, like 2, 3, 4, 5, 6, 7, 8, 9, 10?
No.
Fractions worked that were above above 1?
Yes.
Give me an
It
example.
was like 1.1 under, it was like a mixed fraction.
Okay, so you said, what if it was like 1.2? 1.2 to the x. So we go to the table. Is that growth or decay? It's growth, right? It's increasing throughout the values of y. If you look at the graph,
That's pretty cool.
it's slow growth, but it's growth.
It looks like steps going into the distance.
Yeah, it's pixelated, right? Okay, so that was 1.2, and 1.2 gave us growth. Did you try any fractions?
Yeah.
Like no whole number at all, just like.
Oh, I get what you're saying. Like a fraction that doesn't have a mixed number? Did you try one?
I did 0.99 repeating.
0.9 repeating? Okay, let's just do 0.9. Let's try that. There's the graph. It's kind of hard to see on the graph, but I hope you can see the relationship. Here's the table, which gives us a better understanding. When b was 0.9, was that growth or decay?
Okay.
Decay, okay. Did you try any other numbers?
Oh, I did one. I tried the 1/5 was decay.
You tried 1/5. How did you enter 1/5 into the calculator?
Well, I did 1 times parentheses 1 divided by 5,
Divided by 5.
and then the raised to the x.
Did you put the parentheses out, like inside and then to the x, or did you put the to the x underneath the parentheses?
And you put the parentheses before the.
Okay, yeah, that's what I meant. Okay. And when you did that, you got decay, okay? And the graph looked like this. Are you seeing sort of a general pattern that all the graphs take on the same shape? Some of them are steeper than others, but they're always sort of like a J-shaped curve, okay? So we found that when we used fractions, like what did we do? 0.9 and 1/5, we had decay. But when we used fractions like 1.2, we had growth. What's the difference? Why was 0.9 or 1/5 decay, but 1.2 was growth? DJ?
Because 1.2 is over 2 and the other 2 are below. I mean, 1.2 is greater than 1 and the other 2 are lower than 1.
Okay, so 1.2 and all these numbers, they're greater than 1, but these numbers are less than 1. And that's the difference? What do you guys think?
Yeah.
Yes, agree? Can you explain why?
Because if it's less than 1 and you're multiplying by it, it's almost like you're dividing.
Ooh, I like the way you said that. So you said if b is less than 1, it's almost like you're dividing, because you're multiplying by a fraction where the denominator is larger than the numerator. So you end up dividing, right? Okay, so if we want to find growth, then we have to use a number greater than 1. Why do numbers greater than 1 show growth? Why do numbers that are greater than 1 lead to exponential growth? What do you mean? They go up when you multiply. If you multiply by a number larger than 1, then it's going to increase. Let's think about that. If I multiply something by 1.5, it's now 150% of what it was before. Right? If I multiply something by 2, it's twice as much as it was before. But if I multiply something by 1/3, well, now I divided it, and it's smaller than it was before. So the numbers that are greater than 1, they show growth, where numbers less than 1 show decay. But was there any limitation on how much less than 1 those numbers could be?
Wait, does that mean it went on the other side of the line with graphic?
Like 0.1.
What do you mean, like it went down like this?
Yeah.
That just means that A was negative,
Okay.
because then your y-intercept is below the x-axis.
Okay.
Was there any, well, I'll just leave that there. Was there any minimum constraint constraint for exponential decay? Did you test out 1 itself?
Yeah,
Yeah,
and
it
it went
went
one
straight.
all the way through.
1 didn't work?
No.
So when b equaled 1, we had a
One.
relationship that was linear. Were there any other values that
0.
created a linear relationship?
Oh,
Ref?
wait, no. I was gonna say 0, like 0 all the way down.
Yeah, that's linear,
Oh,
right?
okay.
Okay, so when b equaled 0, it was not exponential. Kylie, did you find any others? Negatives, good. Just all negative numbers. What happened when you put in a negative value for b?
It was like,
It was on the other.
It'd be on the bottom of the graph.
It'd be the bottom of the
graph.
graph.
Okay, let's put in negative 2. Let's just try that. Make sure you put your negative sign in parentheses, right? Because the parentheses mean that the base number is negative, not find the exponent then make it negative. That's not the same thing. The order of operations are that you want the base to be a negative number, so you put that in parentheses, and then the exponent.
But isn't B always supposed to be positive anyways?
Yes, and we're trying to figure out why, right? This is a value that doesn't work in an exponential function. Let's look at the table and look at why. Look at the numbers. 1, negative 2, 4, negative 8, 16, negative 32. Is that increasing or decreasing? It's not doing either, right? Yes. Okay, so Daniel just sort of gave us a drawing in the air of what it looks like. It's kind of like this. Right? The values are sort of flip-flopping with their signs and getting bigger each time, further away from 0 each time. So that's not exponential, right? That's not it. Okay, so going back to our summary. B can't be negative, B can't be 1, B can't be 0. But if it's greater than 1, it's okay, we have growth. If it's less than 1, it's okay, we have decay. But there's got to be another lower bound. B can be less than 1 up until what point? How do you describe negatives just using a number? What's the boundary for the negative numbers? 0. Good. 0. Yes, 0. Very good. Okay, so let's summarize our findings, and I'd like you to write this down, and this is the end of what we'll get to today. Okay. But write this down. This is the summary of what we learned in class today. We have 2 different types of exponential functions, growth and decay. The characteristics of each can be located using an equation, a graph, or a table of values. There's 3 different representations. The information you can get from them is given here in the table. Please write it down. We'll discuss it more next class, and we'll do some more investigations with it.